Hi everyone, welcome to part 2 on our video lecture for section 10.4 on the divergence test, integral test, and p-series test. So for this video, we're going to continue on with a problem that we left off before. So we have the infinite series going from 2 all the way to infinity for the ln of n over n. And we wanted to see if we could use the integral test. Well, as we did for the other examples, we're going to make sure that we're able to use the integral test by making sure that the function is positive, continuous, and decreasing. So let's see, rewriting this one here as a function, we're going to get f of x is equals to the ln of x all over x for values of x that are greater than or equal to 2. Alright, so this one here is a continuous function. It is also positive past the x value of 1, but now we want to see if it is decreasing. Well, taking that derivative for this one, so we're going to get f prime of x is going to be equals to, now this one does require us to use the quotient rule, so we're going to have x times the derivative of the top, which is 1 over x, minus the derivative of the denominator, 1, times the ln of x. And all of this one here is being divided by x squared. Simplifying a little bit here, we can cancel the x's, and we're going to be left with 1 minus the ln of x all over x squared. Now this one here, you're noticing that it's not as easy as the others, because we're not quite sure whether it's going to be decreasing or not. Well, we can go ahead and set up the inequality. We want to figure out for which values of x is my derivative less than 0. Okay, so since the denominator doesn't quite matter whenever you're setting a fraction equal to 0, and for that matter, the denominator here is always positive, so it's not going to be affecting our answer. So, focusing only on the numerator, we're going to have 1 minus the ln of x is less than 0. So, rewriting this one here to solve for the ln of x, take away 1, take away 1, we're going to have a negative ln of x is less than a negative 1, dividing by a negative, and being especially careful that whenever we divide by a negative, we have to flip our inequality symbol. We're going to have the ln of x is greater than 1. Now, getting the x by itself, by exponentiating here, we're going to have x is greater than e, which is, again, about a 2.7. So this is telling us then that our function is only going to be decreasing whenever x is greater than about 2.7. Now, at this point, we run into a little bit of a problem because, well, we're starting at 2. So it doesn't seem like the function is decreasing. So what can we do then? Well, we can do the following. We can actually split up our our series here. Now, what do I mean by that? Well, if I have the series going from 2 to infinity for the ln of n over n, I'm going to go ahead and evaluate the first term. What would be the first term for this one? Well, the first term is going to be the ln of 2 divided by 2. So this is the first term, but what about the remaining terms? Well, I'm not going to go ahead and evaluate the remaining terms, but I'm going to go ahead and continue on with my series. However, as I start off my series, what should be my n? Alright, so I'll let you pause the video here and think about it. Welcome back. So hopefully you guessed it right. The value for n now should be 3 because we already used one of the terms. We already evaluated at n equals to 2, so the next term in the series would be starting at n equals to 3. So we're going to have here the series as n goes from 3 to infinity for the ln of n all over n. Okay, now since we are now starting at 3, we know that the ln of n over n, if we treat it as a function, the ln of x over x, it will now be a decreasing function. So we could use the integral test. Okay, so let's go ahead and use the integral test. So for this one, we're going to go ahead and rewrite it here as the integral from 3 to infinity for the ln of x all over x, which is going to give us here the limit as b goes to, infinity, for the integral from 3 to b of the ln of x all over x. Now, it looks like I'm going to go ahead and need a little bit more room, so I'm just going to make this a little bit smaller here. There we go. Rearrange things here a little bit. Alrighty, so let's go ahead and figure out what will be our integral. So if we're dealing with the integral from the ln of x over x, dx, and I'm going to go ahead and ignore the bounds for now, this looks like a simple u substitution. I'm going to let my u be equals to the ln of x, so that my du is equals to 1 over x dx, which is exactly what we have here. So this one is then going to become the integral for essentially just a u du, which will then give us a u squared over 2. Alright, so this means then that this integral is going to give us the limit as b approaches infinity for our u squared, but the u was the ln, so it's going to be an ln of x, whole thing being squared, divided by 2, and we're going to be evaluating this one here at 3 and infinity. Okay, so let's continue on here. I'll continue it here. So evaluating our limits, oops, again, this one should have been a b. I'm getting a little bit carried away. Alright, so for this one, we're going to have the limit as b approaches infinity for the ln of b squared over 2 minus the ln of 3 squared all over 2. But this one here, since b is going to infinity, then this term is going to infinity, so this integral diverges. So what does this tell us about our series then? Well, it's telling us then that this particular series will diverge. And remember, as we saw in our previous lecture, if you split up a series as two series, and if one of them is diverging, then the whole series is diverging. Therefore, our series, as n goes to 2 to infinity for the ln of n over n, is diverging by the integral test. Alright, so this example was a doozy, but good news, the next couple of examples are going to be a breeze because we're now going to be dealing with p-series. So what is a p-series? Well, a p-series is just a series of the form 1 over n to the p, which is going to give us 1 plus 1 over 2p plus 1 over 3p and so forth. And the good news is that we will instantly know if this series is converging if the p-values, aka the powers here, are greater than 1. And the series will be diverging if the values for p are less than or equals to 1. That's all that we need to know. Similar to geometric series where you can immediately tell if it's going to be converging or diverging depending on the common ratio. And as you saw, those problems were not too bad. Alright, so let's take a look at a couple of quick examples here. So let's say that we have the following series. The series as n goes from 1 to infinity for 1 over n squared. Hey, wait a minute. We encountered this one before. We saw it right here. Now we already know that this one was converging, but we did it through the integral test. However, notice that this one was a p-series with a p-value of 2. So if the p-value is greater than 1, we know that the p-series converges for p-values greater than 1. And for this one here, the p was equals to 2. And that's it. It's that easy. Now taking a look at the next example, we have the series as n goes from 1 to infinity for 1 over the square root of n. Now we really haven't seen that example before, but, well, we can go ahead and rewrite this one here. Actually, I'm not going to go ahead and rewrite it. I'll just point out that the p-value is equals to 1/2, and that this one here is a p-series. So we know that this one here diverges, since our p-value is less than or equals to 1. Okay. So let's take a look at 2 more examples. Actually, a couple more. Let's go over 3 more. Alright, so example C. So we have the series as n goes from 2 to infinity for n raised to the negative 1.001. Now this one here, we will rewrite it. So we have here the sum as n goes from 2 to infinity for 1 over n raised to the 1.001. There we go. Now it looks the way that we want it. This one here is a p-series. And what is our p-value? So it looks like for this one, the p-value is equals to 1.001, which is, lucky for us, greater than 1. So the series will be converging. Okay. Now, this next one, again, it doesn't quite look like a p-series, but we can go ahead and rewrite it to make it look like a p-series. So for this one, I'm just going to go ahead and focus on the powers. So for the numerator, I have the cube root of n squared, but we know that the cube root for n squared is equals to n to the 2/3, and the fourth root of n cubed is the same thing as n to the 3/4. Alright, so if we have a ratio of the cube root of n squared and the fourth root of n cubed, then we can simplify that, and I'll do it here. So n to the 2/3 divided by n to the 3/4. Now, which of this ones is bigger? So the 3/4 is a bigger fraction, so I'm just going to bring the n to the 2/3 down, which is going to give us 1 over n to the 3/4 minus 2/3, which is going to give us 1 over n raised to the 1/12. Okay, so now we get to see here that it is indeed a p-series with a p-value of 1/12, which this one here is less than 1, so this one will end up diverging. So let's just go ahead and rewrite the whole series here as a p-series. Now, we have a 5 here, and just to get you guys more familiar with the properties of series, since it's a constant, I'm going to go ahead and take it out. So we're going to have a 1/5 times the sum as n goes from 1 to infinity for 1 over n to the 1/12, and this one here is a p-series that will be diverging since the p-value is less than 1. Okay, so now let's take a look at another example. Now this one here, I would say it looks a little bit trickier because it doesn't quite look like the p-series, since the p-series would only be 1 over the square root of n. So what can we do here? So I'll let you pause the video for this one and think about it, but I'll give you a hint. Can you rewrite the series in a different form so that it's matching the form of a p-series that we want? So I'll let you pause the video now, think about it, and say, okay, well, can we rewrite the series here? Now, I'll give you another hint, I guess. You can manipulate the index of summation. So think about it there, and we'll come back to see the answer. Welcome back. So we want to go ahead and rewrite the series so that it has the form 1 over the square root of n rather than the form 1 over the square root of n plus 2. So which should be our n value here? Now, if you think about the first term on the original series here, the first term is, put here, the first term is going to be 1 over, if n is 1, then you're going to have 1 over the square root of 3. So if we want the first term to be 1 over the square root of 3, which should be our n value for this one, well, the n value should be 3. And there we go. By shifting the index here, we're able to rewrite the sequence the series in a way that we want. Now, another approach that you can use, and that's the one that I mentioned in class before, is that if you wanted to, let's say, get rid of this plus 2, well, we could have subtracted 2 from the n. But if we subtract 2 from the n here, we need to add 2 on our index here. And the end result is the same. We would still be ending up with a 3 here. Okay, now I'll let you guys ponder it a little bit more. Depending on the approach that you use, I mean, it's completely up to you. I prefer to think about, hey, which n should I pick so that I get the same first term? Alright, so now with that said, we do get to see here that it is now a p-series with a p-value of 1/2, which is less than 1. So this particular series will diverge. Okay. Alrighty. So, with that said, let's take a look at one more problem here. I would say it's a little bit easier than the one that we just did. This one is asking us for which values of a does the series 1 over n raised to the 3a plus 2 converge. Now notice this one is looking like a p-series. Now if it's a p-series, then it looks here like our p-value is 3a plus 2. Now if we want this to converge, then we want this expression to be greater than 1. So at this point, we just need to go ahead and solve the inequality. So solving the inequality, we're going to have here a 3a is less, or is greater than a negative 1 divided by 3 divided by 3. So a is greater than negative 1/3. So if we want this series to converge, then the a values have to be greater than 1/3, negative 1/3. And there we go. That's it for this problem. We are done with section 10.4. Now we're ready to begin section 10.5, which is going to be dealing with more tests. So I'll see you in that lecture. Have a good one.